Hello everyone, welcome to module 3 of this course on microsensors and nanosensors, where we are discussing principle of sensing. This is the third lecture of this module. In the first two lectures, we have seen two different physical principles, particularly capacitive principle and inductive. Okay, we have seen that how a capacitor, particularly parallel plate and core shell kind of spherical or coaxial kind of cylindrical capacitors can be used as a sensor, particularly for humidity sensing, proximity sensing, pressure sensing and displacement sensing. Similarly, for inductive principle also we have seen the basic principle behind operation of a inductance, and we have discussed self-inductance and mutual inductance. Now, in this third lecture, we are going to discuss resistive sensors. As I have mentioned in the previous class also, that resistive sensors are essential because of its CMOS compatible behavior. Okay, it can be integrated with the current technology on which these CMOS are fabricated. Okay, let's try to understand the properties of a wire which is having some resistance. Okay, or let's try to understand this phenomena resistance. Okay, the basic question is, resistance is a characteristic of a material or a device. Okay, it's a property of my sensor, or it's the property of the receptor material that I am using. Okay, so basically the answer is it depends on both. It depends on material as well as the geometry of the resistor. Okay, we'll see how a resistance depends on material as well as the device geometry. Please remember that we have discussed geometry factor for inductor as well as for capacitor. Okay, so materials can be characterized by its resistivity, and this is resistivity is defined by the vector form of Ohm's law. Okay, quickly we'll see what is Ohm's law in its regular definition and in its point form. Okay, so at constant temperature, the potential difference across a current carrying wire, particularly conductors, is directly proportional to the current flowing through it. Okay, or I can write that V is directly proportional to I. Say for I have say this wire and I have applied some potential. Okay, and for this kind of proportionality thing, if I introduce a constant R, okay, this R is known as resistance. Fine, this is I think out in class 10 or before. Okay, however, there is one more definition of Ohm's law, which is known as point form of Ohm's law or a vector form of Ohm's law. Okay, the point form or vector form of Ohm's law is used in mostly in electromagnetic theory, and it says that the current density is directly proportional to electric field. Okay, for this equation or for this proportional thing, if I introduce a constant, it is the conductivity, right? So J is equal to sigma into E. Okay, where sigma is the electrical conductivity of the material. Okay, this is the point form of Ohm's law. Okay, and we know that resistivity rho is related to this conductivity as sigma is equal to 1 by sigma, right, where rho is your resistivity. A material can be characterized by specific resistivity rho, or sometimes we also call it resistivity. Okay, this rho is, as it comes from this equation, E by J. Okay, sigma is J by E, and as I have mentioned that rho is 1 by sigma, so resistivity is E by J. Fine. J is the current density, and when I say density means current per unit area. So if I have to calculate the current density for a wire of cross sectional area A, I can write J is equal to current divided by the cross sectional area. Okay, or I by A. All right. So resistivity of a material from the material point of view can be written as m by ne square into tau, okay, where m is the mass of electron. Particularly I am seeing this for a conductor and say metallic wire, okay. M is the mass of the electron, n is number of conduction electron per unit volume, E is charge on electron or 1.6 into 10 power minus 19 coulomb, okay, and this is tau, not rho. Tau is the mean time between collisions, okay. So resistivity can be calculated like by this formula, m by ne square into tau, where tau is the mean time between collision, E is the charge of an electron, m is the mass of an electron, while n is the number of conduction electron per unit volume in that particular conductor, okay. So resistance can be expressed by this particular formula. R is equal to rho into L by A, where A is the cross sectional area, L is the length of the conductor, rho is your resistivity, okay. And similar to the capacitance, where we have defined for a parallel plate capacitor, we have written C is equal to epsilon naught A by D, and we have called this A by D as geometry factor G. So C was equal to epsilon naught into G. Similarly, we have defined for inductor. For resistor, the L by A is the geometry factor, okay. This is called as G. So R is equal to rho into G, okay. To design a resistive sensor, we have to find the ways by which we can modulate either the specific resistivity or the geometry factor of the resistor. Of course, the geometry factor includes two parameters, the length and the cross-sectional area. If we can modulate any of these three parameters, either rho, L or A, and if I am able to detect that, okay, I can make a resistive sensor, okay. We will see some example that how these properties can be modulated and what kind of sensors we can develop using these simple resistors, okay. Usually the specific resistivity and conductivity of a material is not constant, okay. It is basically property of temperature, okay. It changes with temperature. The equation is very long on temperature dependency, but for the simplified form can be written as rho is equal to rho naught into 1 plus alpha T minus T naught by T naught, where T naught is the initial temperature and T is the final temperature, okay. Rho naught is the specific resistivity at a reference temperature, okay, and alpha is known as temperature coefficient of resistance, or we call it TCR, okay. So rho is equal to rho naught into 1 plus alpha T minus T naught by T naught, okay. There are other factors also of T minus T naught by T naught, but I am ignoring all of them, okay, and in the simplified form I have written it, okay. In a larger range, resistivity is a non-linear function of temperature, but I am bringing it to this area, okay, to this narrower range, okay. Within this kind of relatively narrower range, it can be approximated linearly using this alpha function, okay, or using this TCR, okay. Now let us see some of the example of the sensors that can be made using these resistances, okay. First, let us try to understand the strain sensitivity of the resistances, okay. So when a material is mechanically deformed, its electrical resistance changes, okay. Mostly it happens with all kind of materials, okay, but for some it is very prominent, okay. Mechanical deformation modulates either the specific resistivity or the geometry factor of the material, okay. So strain sensitivity is basically known as piezoresistive effect, okay. So we are not studying this piezoresistivity separately, but we are discussing this under the heading of resistance, but we will discuss some sensor which are based on piezoresistive principle in this course, okay, in module 5 or 6, okay. So usually good resistor will be stable, whereas a bad resistor provides opportunity to make sensor, okay. Similar to this, we have seen in when we discussed capacitors also, that in laboratory or in electronic circuits we need good capacitances, but for sensor development we need bad capacitances. Similarly, here also for laboratory application and others, we need a very good resistor which doesn't change its properties with conditions changing in the ambient. Say if the temperature of the ambient is changing, or a pressure is changing, or say relative humidity is changing, the resistance value is constant, okay. So they are good resistances, and for this course they are not desirable, okay. We need bad resistances which can change its properties, but only condition is it should come back to its original position when the stimuli is removed, okay. So strain sensors can be built using resistance or using this piezoresistive effect, okay. And strain sensors are the backbone of many force sensors and many pressure sensors, okay. So these resistive devices are very crucial for strain gauges, okay, or strain sensors, okay. We know the relationship between the applied stress and the force, and this sigma is given as, or the applied stress is nothing but force per unit area. So F by A, or it is given as E into dl by L, where dl is the deformation or change in the length and L is the actual length, while E is the Young's modulus of the material, okay. The ratio dl by L is known as strain, and we are denoting it using E, okay. Basically this is the normalized deformation of the material, okay. So strain is this E into dl by L, okay. Consider that a cylindrical conductive wire is stretched by a force F, okay, as you can see over here. This was the original wire, okay, with cross sectional area A. Now I am using a force which is stretching it, okay. Now volume of the material remains constant, okay, while the length has increased. Because of this increment in the length, the cross sectional area has decreased. So A has decreased while L has increased in this case, okay. This resistance we know that can be written as R, this R is equal to rho L by A, okay. So if I multiply this A by L, I can calculate volume. So I can simply write as R equal to rho L by A. If I multiply the numerator and denominator with L, I get R is equal to rho L square by A into L. A into L is nothing but its volume. So it is written as R is equal to rho into L square by V, okay, where V is the volume. Now let's differentiate this R with respect to L, okay. Let's find the sensitivity of this resistance, okay. So the sensitivity of the resistance along the wire elongation can be simply found by dr by dl, which gives 2 rho by V into L, okay. If you see this, sensitivity increases for the longer and thinner wires with the high specific resistances, okay. Now the normalized incremental resistance of the strained wire is linearly related to the strain, and it can be written as dr by R directly proportional to E. If I include this SE, which is a proportionality constant, I can write dr by R is equal to SE into E, where E was my strain and SE is the sensitivity of the strain wire, okay. This is the principle behind the strain gauges, okay. Usually this sensitivity is in the range of around 2 to 6 for metallic wire. However, for semiconductors it is very high. Usually it is from 40 to 200, and even beyond this also people has reported, okay. So in semiconductors, the geometry factor has a much smaller impact compared to the change in the specific resistivity, okay, due to the deformation of the material's crystal structure. Okay. Now, this is the basis of resistance based strain sensors. As I have mentioned that these strain sensors are also backbone of force sensors and pressure sensors. So now I think that you have understood that how a resistance or a simple resistor can be used for pressure sensing and force sensing through this strain application. Okay. Let's see another example of resistors being used in sensing application, particularly the moisture sensitivity. So, in relation to the environmental factors, the specific resistivity rho of a resistor can be controlled by choosing the receptor material. Okay, the amount of moisture absorbed by the resistor significantly affects the rho value. Okay, a moisture dependent resistor can be made from a hygroscopic material whose specific resistivity is greatly influenced by the concentration of the absorbed water molecules. Okay, and this is the basis of resistive humidity sensors, which we sometimes also call hygrometers or hygristors. Okay. So, a typical hygrostor consists of a ceramic substrate or silicon substrate on which we usually screen print the conductive interdigitated electrode, and in the modern era it can be also patterned using photolithography and other lithography techniques that we have discussed in our initial modules. Okay, the electrodes are metal conductors. Basically metals like gold and platinum are used. Okay, if you go in technicalities, gold cannot be deposited on these substrates basically because of the adhesion issues. Okay, so usually you deposit very thin layer of chromium material, okay, say 10 nanometer of chrome, okay, on top of this say 90 nanometer of say or 100 nanometer of gold. Okay, similarly platinum electrodes very difficult to sustain on silicon substrates, okay, particularly on SiSiO2. So in those conditions we first deposit titanium, say initial seed layer, so say about 10 nanometer, and on top of that say we have 90 to 110 nanometer of platinum. Okay, those kind of electrodes are deposited on the silicon substrate or even on the ceramic substrates because it will avoid any kind of corrosion of the material. So we do not use corrosive material for this electrode formation. Okay, the electrodes and the space between them are coated with a hygroscopic semiconductive gel or powder or semiconducting material suspended in some solvent. Okay, this gel forms a matrix to hold the conductive particles. Okay, therefore it results in the formation of resistor between two electrodes. So you have two electrodes, in between you have gel kind of thing which has some reinforced metal nanoparticles, okay, and it is forming a very good conductive path. Okay, these gels are usually made up of this material hydroxyethyl cellulose. Okay, it is essential to use only symmetrical AC excitations, particularly in these cases, and to avoid any kind of DC biasing, because if you use only AC, you can avoid polarization of the coating. Okay, otherwise if you do DC, there will be polarization and it can damage your device. Okay, but nowadays advanced materials has emerged where this polarization do not exist even with the DC biasing. Okay, very similar to what we have seen for moisture sensors, we have also gas sensors or chemical sensors based on change in the resistance. Okay, very similar to that, you have a substrate. This substrate, as we have discussed, that it can be like silicon, SiSiO2, or it can be sapphire, it can be mica. If the application is for high temperature, you can also have silicon carbide kind of substrate. Okay, it can also be made on flexible substrates. Okay, depending on if the sensing layer is deposable or not. It can be deposited or not. Okay. So you have electrodes, metal electrodes, and you have a sensing layer coated by say some method, say PVD or say CVD or some other method like sol gel or hydrothermal, whatever method you use, and on top you have electrodes and you have substrate. Okay. Now these gas molecules will come and interact with the receptor material. Now mostly these receptor materials are either a p-type semiconductors or n-type semiconductor. So it can be p-type semiconductor or n-type semiconductor. Now these gas molecules can either be oxidizing or reducing in nature. Okay, it can be oxidizing or reducing in nature. Okay, so now say I have a reducing gas, okay, and my film is say n-type material. When I say n-type material means the conductivity is majorly due to movement of electrons. All right. Now this reducing gas will come, okay, near to the substrate, okay, and it will interact through this material. Usually this gas cannot interact directly with the semiconductor. It interacts with some oxygen species. Okay. Usually these sensors are placed in ambient conditions, okay, and depending on at what temperature your device is kept, you have various oxygen species existing at the surface. So when I say oxygen species, I mean to say I can have O negative, I may have O2 negative, I may have O2 negative. These kind of species exist on the surface. Okay. This reducing gas interact with these oxygen molecules, okay, and accordingly the electron, exchange happens between this oxygen and the film. So there should be interaction between this film and the gas, but in between you have a intermediate stage in the form of oxygen. Okay, we'll discuss this under the chemical sensors. Okay, but you have a oxygen species and depending on this material is the receptor material is p-type or n-type or this gas is oxidizing and or reducing, the exchange happens, exchange of electron and holes happens. Okay, so since this was a reducing gas, population of electron will increase in this material. Okay, so basically you are increasing the conductivity or increasing the conductance of the material, or the resistance of the material is going down. Okay, so if you have say initially a resistance R of the material, okay, when these gas molecules come, what will happen is the resistance will decrease for reducing gas, and for say this was n-type material. Okay, and when it is switched off, it come back to its original resistance. Okay, so by this I can find, if I can calculate this resistance change, I can calibrate it against some standard sensors, and I can say that okay, say this much concentration of this gas is present or not. Okay, so this is how a simple variation in resistance of some film, okay, some thin film, can be used as a gas sensor. So apart from that, there are other applications of also of this resistance changes, like particularly in case of say temperature sensors, you have RTDs, very famous RTDs, where the resistance of the material changes with respect to temperature. Okay, and there are other sensors also that can be made based on resistive principle. So with this we will close this chapter or today's lecture. Okay, in the next class we will discuss the piezoelectric phenomena, Okay, and after that we will discuss pyroelectric phenomena, and then we will finish this module 3. Thank you.